Oh, yeah, I forgot about
I'll be super brief, don't worry.
No, it's fine.
This is CHEM 223?
Yeah. Still like 2 minutes.
Oh, yeah,
So.
yeah. Quick for everyone.
Well, I guess we'll get started. So we have a trio presentation, so I'll let her take over.
Hi, everyone. I'm Karen Shaw. I am the program specialist over at TRIO Student Support Services. We're a program here on campus who helps students transfer to universities. So if you are going to be transferring to a university at any point, please come and see us because we have resources for you. If you qualify, you can come in and join the program. We have university tours, academic advising, tutoring, scholarship assistance, and much, much more. Pretty much everything you need to transfer to a university. So if that is your pathway, come join us. We check on all your eligibility and everything for you. So if you just apply online on our website, then we will check on that and we'll be in touch with you. And if you have any questions, we're located over in the Student Success Center across the street in room 8. So come and see us. I'm going to pass around some flyers and some free pens, and then I'll hand it over to you.
Thank you. Yeah, highly recommend if you're eligible for TRIO and you're not already in TRIO, definitely join. It's a good resource. And do you still give lots of free snacks?
We do have snacks, yes. We have many for us. You're already with us.
I know that's what many people appreciate.
No, you're right. Thank you all. I appreciate it.
Thank you. Any other questions about TRIO? Or all right, let's talk about other announcements before we jump into the rest of the chapter. So if you saw the Blackboard announcement, the Oregon Caves trip is officially scheduled for May 9th. I'm still working to nail down a time. I was aiming for kind of the 12:30, 1 p.m. time because of the feedback. They just haven't confirmed, so I'm just kind of waiting. So I guess we'll put tentative. And then you will have to drive yourselves, unfortunately, so that there's no bus. So that's the one thing about community college, right? No budget for a science van, so you have to drive yourselves. And it is like a 2.5-hour drive, or 2 hours. So if you want to carpool, start thinking about that now. Kind of talk about that, arrange that. That's what I'm kind of aiming for. Maybe like 1 p.m. to give us a little more flexibility.
For those of us that can't go, is there still going to be this class on Thursday?
No, so yeah, we won't meet. So yeah, I won't be here because I'll be in the caves, hopefully. And so yeah, no class that day. So I think if I remember from the syllabus, we don't have lab that week either. So the Tuesday lab won't meet, and then we'll just all meet on Thursday. And if you can't make it this day, you can either go separately on another day. So I'll put alternative assignments. And I still need to hand out like a paper for all this. So just kind of putting it on the docket. So you can either go on your own and take a little picture so I know you were there. Or if you can't make it out to the Oregon Caves, you can research another area. So I'll say geologically relevant, if I could spell. So this could be, right, the table rocks or all of the lava formations that are out there, especially around Bend, the lava tube. So anything would kind of be open, and then you'd probably have to write like a 1-page paper on it. Yeah, you probably want to wear pants. Like the cave is kind of cool. It's like the same temperature year round. And if you go on the Oregon Caves website, so I'll send out like more information. But yeah, it says kind of, pack warm or in layers because it will be cool in there. And then I didn't schedule this to like hike as a group, but they're like hiking trails like after, so you could, wander around as well or picnic. So kind of plan that if you want to. So this is one of your labs. So it's either you go to the caves and then you don't have to write a paper because you went on the field trip, basically. Or you go on your own, again, and take a picture, get the tour. And then if you can't make it out there, then your paper is in replacement of that assignment. So probably next week I'll hand out all the paperwork because there's waivers and all that stuff. And I'll probably get a sign up too, just so I know who to expect at the caves and who's going separately and who might be writing a paper. All right, questions about the Oregon Caves field trip?
How long do you think the tour is supposed to be?
I think the tour is about an hour, so yeah, it's not too long. It's pretty fun too, so it's nice. All right, so now we're ready for our chapter. So our last bit is complex ion formation. And so our first statement is transition metals tend to be good Lewis acids. And so just a reminder, what's a Lewis acid again? What was the definition? Yeah, so it has to do, so then if the Lewis acid base had to do with electrons being donated or received, so then what's the Lewis acid, do we remember? So good electron receiver. And so all this means is that we, at least, so this is what I like to talk about my area. And so we can think about ligands binding to our metals. So we're going to look at a demonstration. And so first of all, we have to kind of rethink about how these ions are in solution. So here we have our silver complex. So it's showing that in solution, it actually makes this aqueous complex compound. So meaning in solution, right, our waters are donating. And so this would have to be verified by crystal structure or some sort of analysis to figure out how many equivalents of water. So it's usually what happens. And so these are just called complex ions where, again, some ligand, and so I'm going to use the term ligand. So this just means anything attached to it. So in this case, we're looking at individual water molecules, but they can be more complex. And there's a term here, so ligand. So anytime these compounds, covalent compounds, are attached to metals, they're referred to as ligands. And so, of course, we're going to quantify this. So I guess let's look at the quantification for a little bit. And so now we have this formation constant. And so now we can show our complexation. So again, we're going to look at a similar demo. And so you have your silver in solution. And again, you're thinking about it instead as this aqua compound, this bis aqua compound. And so now in solution, it's going to start replacing those aqua ligands with the ammonia ligands, which turn into amines by name. So that's when ammonia is acting as a ligand, it's called an amine compound. And so then it makes this compound, which is usually indicated by a color change. And then, of course, we can figure out how much we make by, again, surprise, surprise, equilibrium constants. So again, like we've seen, products over reactants. So now it's going to be the concentration of our complex compound over the whatever concentration of remaining silver and free ammonia. Well, let's kind of look at a demo. And so we want to see this in action. Actually, sorry, too many things going on. There we go. So I'll have it like this. And so let's look at our demo. And so we have, and let's start pouring some things out. Too many things. Oh, you can't see this. Where did it go? There it is. All right, so we have copper chloride. I'm going to add some copper chloride. Yeah, hopefully you can tell that in blue. And if you need to get closer in the back, you can. And so let's kind of think about what this really is. So this is kind of the first problem, is our first kind of basic understanding is, okay, we have ions that dissociate in solution, but this isn't the full picture. So what's really happening is that copper, just that blue solution, which disappeared from my screen. There we go. That helps. And so this is actually complexed with water. And so it has 6 water molecules complex, and I'm going to show a representative crystal structure. So it's in kind of the basic octahedral shape. And so these arrows just kind of indicate that the oxygen ligands on the water are donating 2 electrons, so from one of those lone pairs. I just didn't draw both the lone pairs. And so give me a second here. And so here is a similar but not the same compound. So sometimes when people crystallize structures out, there's different counter ions and things that are crystallized. And so what we're seeing here is our copper 2+ in solution, complex with our 6 water ligands. So you can see that. So they actually, again, they crystallize this out, and then it has these other compounds. So you can see they're pyrazine dioxide molecules, and then BF3. So BF3 is just used to help crystallize ions, but this is what we want to focus on. So really our copper 2+ in solution is already complex with water molecules acting as ligands to help solubilize and stabilize it. So that's really what copper 2+ in solution is. And so now let's look at what we're going to do to it. So now we want to add, so let's look at our reaction. So now we're going to take, and I'll just simplify it for now, so we're going to take copper 2+, we're going to add ammonia, or however you want to look at it, right, ammonium hydroxide. So just kind of an aside, we're thinking about, well, ammonia and ammonium hydroxide are of course interchangeable. So in solution, we're going to have hydroxide ions. And so initially what's going to happen is, again, we're going to react just oversimplifying our hexaqua compound, and then we're going to add 2 equivalents of hydroxide to make our insoluble copper hydroxide compound. So let's see if we can do that. Now I'm going to add some ammonium hydroxide. Uh-oh, I okay. I might run back to the stock room and get a more dilute ammonium hydroxide. So let me bring it back. So I added some acid. That might be okay. Let me go run and get some dilute. I don't want it to go too fast. All right, let's try. I think my 0.6 is too much. Now if I add 0.3 molar. So it's starting to get a little cloudy. You'll see that? So let's add a bit more. So that's just our copper. There we go. That looks better. So that's our copper hydroxide. An insoluble, whitish. You might want to get, again, closer if you can't see where you're at. And so again, now we made this copper hydroxide compound. And so you saw it when I added the 6 molar ammonium hydroxide for a second. But then we're going to keep going, and then we're going to make our amine complex. And so we are going to attach 4 ammonia ligands. So I might switch back for 6 molar. And so there, that very blue, you see that deep blue that's coming out. So let me add some more again. And get it fully converted. So you can see kind of the hydroxide solids in there. Stir it around some more. There we go. So now it's making that deep, deep blue that you're seeing. That is the copper for amine. And so I'll keep converting it. So right now you can see there's a mixture because I didn't mix it very well. So, you know, if you want to do this on a bigger scale, you probably want to stir bar. And so there's probably some copper hydroxide. And then just keep converting it so it's all mixed to the deep blue amine. So that's just one example of, again, a complexation reaction. And so we could, of course, quantify that if we were measuring our materials more carefully. And so kind of what we'll see too is, so you might look at some reactions and you're not sure what happens. And so this is a good reference kind of to give us a hint. Because again, right, we might not know, well, how many ammonia ligands are going to attach to copper, but then it's showing us, okay, this is a common copper. And, you know, because you wouldn't know that these compounds tend to make either like square planar or octahedral complexes, so square planar is pretty favorable as well. And so again, just another idea of all your different ligands. So cyanide, ammonia, of course, with cobalt. Cobalt does a lot of ligand formation. And then we can, of course, appreciate their Kf constants. And so some of them are pretty high, so pretty favorable. And we can see that right for that copper amine reaction. So that is a pretty high Kf. And, you know, we saw we were able to get a nice conversion to the deep blue there. All right, so now let's do some math. Less exciting, but necessary. And so see if we can figure out how you might kind of set this up, because we're just building upon our same kind of rice table equilibrium ideas. And so now we have a 200 milliliter sample of solution. That is 1.5 times 10 to the negative third molarity in copper nitrate. And then you mix it with a 250 milliliter sample of solution that is 0.2 molar in ammonia. So after equilibrium, what is the concentration of copper? So let's kind of start talking about it. And so what did you guys think to do first? What are some steps, especially with what they gave us? What do we need to do? So did we write our reaction first at least? So what do we get for our reaction? And then, so how many equivalents of ammonia? So 4. And so writing out, again, you can refer back to the chart to kind of help us. Well, what is it going to make? Okay. And then what's the next step? So they gave us these amounts and concentrations. Yeah, so you got to start by finding moles of each. So I think some people did that. So let's do that. Let me pull up my calculator. So for copper, that's 1.5 times 10 to the negative third, multiplied by 200 milliliters, or 0.2. So do we get 3 times 10 to the negative fourth for moles of copper? And I'll just kind of write moles so we know we're in moles right now to do our stoichiometry. And so then let's find moles of ammonia. So 0.2 times 0.25, so just converting that to liters again. So then 0.05 moles. Then we can do our change. And so again, from our initial conditions, we have no product, so we have to make at least X of product, and then minus X of copper, and then how much ammonia do we lose? 4x. Yeah, so minus 4x, so just make sure you watch that stoichiometry. Then we can do equilibrium conditions. And then set our KF. So let me go back and get that value. So we said 1.7 times 10 to the 13th. And I'll just rewrite what our KF expression was. So just putting our products, so our copper tetraammonia complex, or amine tetraamine complex, over copper 2 plus, over ammonia concentration. So now just plugging in my variables. And so now let's think about what kind of assumption we can make. And any thoughts on that, especially given our KF? So remember that was kind of large. So what could we assume? So I guess compare the amounts of copper versus ammonia, and then also kind of thinking about this. So we could make, and this, if you remember, this is kind of what we did in the equilibrium lab when we were trying to set up our calibration. Remember we said, like, let's make the iron concentration so tiny that all of it is converted to product. So that same assumption is happening here. So we're going to assume that all of our copper 2 plus is converted to X. So that means X is 3 times 10 to the negative fourth for a concentration of copper. And so now we can figure out how much ammonia is left over. Except we need times 4, right? So times 4. So this many moles. But then what's the next issue? So now we're in moles, right? So what's our total volume? So 0.45 liters. And so now we gotta readjust everything. So these were in moles. And so we want to solve for how much copper is left over in theory. So now we have to do 3 times 10 to the negative fourth, right? Because that was X over 0.45 liters. So find our molarities. So basically we need to calculate all our molarities. And then same thing, our moles of ammonia. So we subtracted, so 0.0488 over our liters as well. And then we want to solve for X, which gives us, right, a small amount of copper left over. So let me catch up on the math. So just converting this to concentration in molarity now, so we can plug that in. That's concentration of product, and then figuring out how much ammonia was remaining. So 0.108 molarity. So now we can solve for X to figure out what negligible amount of copper we have. Oops, yeah, that looks right. So is this what people got? And it should be something kind of like silly tiny, right? Because we assume most of it was converted anyway, so there should only be a small concentration of copper left in solution. So we get our copper 2 remaining after equilibrium is about 3.6 times 10 to the negative 16 molarity. Yeah, so let's kind of recap, right? So we were at here with kind of our equilibrium, but we needed to figure out moles and then of course convert this to concentration. So maybe I should write that. So not in molarity right now. So I was kind of working through that. So, right, we assumed that all the copper was converted to the complex, at least for the most part. So then that gave us X moles, so 3 times 10 to the negative fourth. So just the same moles we had of copper. So that was moles of that. Found moles of ammonia, right? So we just subtracted 0.05 minus 4 times our X. Got this number. But then we said, right, we had to figure out our new molarity. So that's where we were here. So let me add that, right? So now this was finding molarity step. So right after we found the moles from our stoichiometric reaction, then divide by total volume. So we found it was 0.45 liters. So again, just adding, dividing everything, and solving for X, which was copper 2+. Does that make sense for everybody?
What I don't get is if we assume that all of the copper was converted, doesn't that mean all of the copper, like, in our calculations, would be converted, and therefore the remaining copper would be 0?
That's what it feels like. So the thing is, right, it's an equilibrium expression, and then there's going to be such a tiny amount anyways, right? So if you do the subtraction, I mean, this is basically negligible with sig figs. So that's why we're able to kind of make that assumption that most of it is converted and then kind of calculate the concentration from that assumption, if that makes sense, since it is equilibrium. And again, right, these concentrations are pretty large, so that's also why we expect these to be small and we can make those types of assumptions. So yeah, again, right, notice for most of these, they have really high values that are going to be pretty favorable for our complex formation.
One thing that just feels weird with me is because you go to like the KF is equal to the ES concentrations, then we assume that say the copper is equal to, or the X is equal to the same amount of magnesium and copper. Looking at the KF, you know, of course, you get like a 0 on the bottom, which just feels weird. Going back up a little bit.
Yeah, I guess I didn't follow where, oh, you're talking about if you take like, yeah, 3 times 10 to the negative 4. That's why we assume that it's X, right? But then you don't have a 0 on the bottom, kind of like you were saying. That's why we go back and resolve for it,
Okay.
but then get, right, a super tiny negligible amount. So, right, again, if you like do, that's basically 0 compared to 10 to the negative 4. You know, we could recalculate or sorry, it started with 10 to the negative third, right, initial molarity. And then we have a very small molarity left. So it's basically 0, right? So it's basically a full conversion. It feels kind of weird, but yeah, that's why it kind of works out.
Okay, that makes sense.
All right, let's look at our last little topic. And again, we'll have another quick demo, assuming I didn't mess up my concentrations again too badly. And so we have, again, kind of how things are soluble. And so let's start off with the statement. So the solubility of an ionic compound that contains a metal ion that forms a complex ion increases in the presence of aqueous ligands. So that's just saying if we can complex it, then we have Le Chatelier's principle. So this is referring to thinking back to solubility. So now this could be a question on an exam, would be like, where is, you know, silver chloride more soluble? And maybe one of the solutions could be adding ammonia, and this would be what it's referring to. So right now we're thinking of solubility. It's of course, right, silver chloride, pretty insoluble, but disassociates to give you some silver and some chloride. But then if you add a ligand that again it can complex with, and that's aqueous, so like ammonia, And same thing, right, just like we saw with the copper. So we started with copper hydroxide, but then we can add amine to it, and that would make it more soluble. So same thing with silver. So we see that same effect, just doesn't make a pretty color. So right, adding our ammonia back in increases our solubility. And so then we come up with this other statement, and this is kind of interesting. And so, of course, many metal hydroxides are insoluble, and we kind of touched on this that, well, we can take those metal hydroxides and add acid, and of course, that shifts our equilibrium. And then it makes this kind of statement, oh, some metal hydroxides also become more soluble in a basic solution. And what's also kind of confusing is if you start looking up things. So aluminum is also known as amphoteric. So do y'all remember what that means? Had this term, I think. Remember? Oh, so can be acid or a base. And so let's kind of break down what this means more. So I brought another demo so we could see this. Because we have some words here, but the demo will hopefully be better. So all right, so let me switch out. All right, so in here, I have some aluminum sulfate. So it's just in solution, right, dissolved. And so we can write out what that is. So it's just aluminum plus, right, just 3 plus floating around, nothing too exciting. And so the idea is now I'm going to add sodium hydroxide to it. And that should make our insoluble aluminum hydroxide compounds. Let's see if we can do that. Sodium hydroxide. And so we see our cloudy formation going. And we might have to get closer to see. Make sure that's all separated. Oops, So did you see that? It happened kind of fast, but I went too far. Let me see if I can take it back. So I'm adding acid back in. And so right, I added acid because I'm trying to bring it back. There we go. Now it's cloudy again. Kind of hard to see. And so what happened there, we'll do it again because it was kind of quick. And so I made this, but then I kind of overshot it a little bit because I wasn't sure if it fully precipitated out. And if you keep going, so now aluminum hydroxide, and you add another equivalent of hydroxide to it, it actually makes now an aqueous compound. And so now this is aqueous and went back in solution. And so, right, we can see that again and kind of play with it. And again, if you want to get closer so you can see it happening better, feel free. So right now it's a little cloudy in solution. Kind of hard to see. I don't have anything dark on me. Trying to see if I have a darker background. That helps. You kind of see how it's cloudy. Okay, I'll hold that so you can see. And so now I'm going to add sodium hydroxide again. And boom, you notice how that solution clears up once more, making that aluminum hydroxide with 4 on them now. And so then, right, we can see that one more time. So let's add our acid. So of course now it's going to bring our pH back down. And so you can see that aluminum hydroxide being formed again. And so now it's cloudier, sorry, with that aluminum hydroxide. And if I take it too far, then of course I'll neutralize it right back to the free aluminum. Now, maybe I've gone too far. So let me add sodium hydroxide again. And so it's kind of getting cloudy. So there we are back at our aluminum hydroxide solids now, reputting it. And so that's what it's referring to now, right, when we see that kind of amphoteric behavior, right? So we're saying, well, we can start with aluminum hydroxide. It can be cloudy. We add acid to it, right, and then it goes in solution. So, of course, that's aluminum hydroxide reacting with acid. And so I guess we could re-summarize if we wanted to. So kind of basic re-summary is, so now we're saying, and why people say aluminum hydroxide is amphoteric, is we can have our aluminum hydroxide, right? It can react with our hydrochloric acid and then just give us free aluminum and, of course, water floating around, so we saw that. Or we can add our base to it and then push it all the way again to our aqueous tetrahydroxide compound in solution there. Oops. Yeah, so that's when it goes transparent again with the hydroxide, exactly. So we could see that, right, so right now it's at a 3-hydroxide species. So if you want to see me push it again, we could do that. Then there'd just be a competition, right, between like copper hydroxides, copper. I don't know if it'd be that exciting. And so that's what it's kind of showing again here. And once again, similar ideas that really our aluminum is complex with water in solution. And then technically you do one equivalent at a time. So, right, of course, you exchange one water for a hydroxide. We wouldn't notice a change, though, because it's still in solution, but just thinking stepwise. Then you add, right, your next equivalent. So still aqueous, so 2 would be complexed. And then continue, so once you get to that third equivalent of hydroxide, that's when we see the solid come out. And then again, right, just go back and forth with that. All right, so hopefully that made sense and helped. Any other last minute thoughts or things on this chapter? All right, we're probably good to end lecture there, and we have our quiz, of course, so I'll give y'all a 10-minute break. If anybody's super antsy to start the quiz, I guess you can let me know, but otherwise I'll hand them out at noon. So I will stop this.